Hello everyone. We will be discussing today 3 raised to k factorial design. In 3 raised to k factorial design, we have k factors in generals, each at 3 levels. And these levels are denoted by the sign -101 or 0, 1, 2. Unlike two-level factorial design, where we assume that a response varies linearly with the change in the level of the factors, three-level factorial design allows modeling of quadratic relationship between the response and the design factors. So we start with a particular case of 3 raised to k factorial design. Suppose 3 raised to 2 factorial design. Suppose we have two factors a and b. Each of the factors are at 3 levels, producing the 9 treatment combinations of the 3 raised to 2 factorial design. 1a and a square. Then we introduce b and multiply it with a and a square, which produces ab and a square b. Then we introduce b square and multiply it with a and a square, which produces ab square and a square b square. Calculating the main effect in case of two-level factorial design is quite intuitive, as it is difference between the average response at high level and low level of the factor. But in case of 3 raised to k design, as each factor has 3 levels to account for the curvature in the response, the linear effect and the quadratic effect together represent the main effect of any factor. Unlike the two-level factorial design, the main effect is composed of the linear effect and quadratic effect. Before computing the linear and quadratic effect of these factors, let us introduce some notations. Let A0 be the sum of all those observations at which factor A was at low level. So this is actually equal to sum of 1 plus b plus b square. A1 is sum of all the observations when factor A is at intermediate level. So this is sum of A plus AB plus AB square. And A2 is sum of all the observation when factor A is at high level. So it is sum of the treatment combinations A square b and a square b square. Similarly, b0 is sum of all the treatment combinations or yields for which the factor b was set at low level. So these treatment combinations are 1a plus a square. b1 is sum of all the yields for which the factor b was at intermediate level. So it is sum of the treatment combinations b, ab and a square b, and b2 is sum of the treatment combination when factor b was at high level. So b square, ab square and a square b square. Now we can compute two effects of factor A. Those two effects are A1 minus A0 and A2 minus A1. These two effects now will be utilized to find the linear and quadratic effect associated with main effect of factor A. The linear effect of factor A I denote by A subscript L, and this is actually the sum of these two linear effects, which is A2 minus A1 plus A1 minus A0, which turns out to be A2 minus A0. The quadratic effect associated with main effect of factor A I denote by A subscript capital Q, and it is the difference between these two effects. So it is A2 minus A1 minus A1 minus A0, and this is equal to A2 minus 2A1 plus A0. Similarly, the linear effect associated with main effect of B is B2 minus B0, and quadratic effect associated with main effect of B is B2 minus 2B1 plus B0. Now we will put the values for A0, A1 and A2 to find the linear and quadratic effect of main effect of factor A. So AL is now equal to A2 minus A0, and A2 is A square plus A square B plus A square B square minus B square plus B plus 1. This, if you simplify, becomes equal to A square minus 1 into B square plus B plus 1. Similarly, the linear effect of B is, see, the sum of all the yields when B is at high level minus the sum of all the yields when B is at low level. So it is B square plus AB square plus A square B square minus A square plus A plus 1. And this, if we simplify, becomes equal to A square plus A plus 1 into B square minus 1. Now we find the quadratic effect of factor A. The quadratic effect of factor A is AQ equal to A2 minus 2A1 plus A0. Now A2 is sum of all the yields for which factor A is set at high level. So A square plus A square B plus A square B square minus 2 times the sum of all the yields for which factor A is at intermediate level. So A plus AB plus AB square plus sum of all the yields for which factor A is set at low level. So we have 1 plus B plus B square 1. This, if we simplify, becomes algebraically equal to A square minus 2A plus 1 into B square plus B plus 1. Similarly, the quadratic effect of B will be B2 minus 2B1 plus B0, which will be equal to B square plus AB square plus A square B square minus 2 times B plus AB plus A square B and plus 1 plus A plus A square, and this simplifies to A square plus A plus 1 into B square minus 2B plus 1. Remember that these formulae, these algebraic expressions, cannot be used directly to compute the effects or contrast, because these are mere algebraic simplifications. In order to compute the effects, these expressions must be simplified, that is expanded by multiplying the bracket, and then you will get the linear combination of the treatments, and then we have to feed the values for the yields. In place of every treatment combination, we will get the effect. Now we will discuss the various interactions associated with 3-level factorial design. The interaction AB has 4 components. It is composed of ALBL, which represents the interaction between linear effect of A and linear effect of B. Similarly, ALBQ represents the interaction between linear effect of A and quadratic effect of B. AQBL represents interaction between quadratic effect of A and linear effect of B, and finally AQBQ represent the interaction between quadratic effect of both the factors. To compute the effects for these components, let us start with AL and BL. To compute ALBL, first we will find the linear effect of B at different levels of A. So at higher level of A, the linear effect of B is A square B square minus A square. Note that the factor A is at higher level and the level of factor B changes from low to high, because we know that the linear effect of B is B2 minus B0. Now we find the linear effect of B at intermediate level of A. So A into B square minus A. Again, factor A is set at intermediate level and factor B changes its level from low to high, and then linear effect of factor B at low level of A, which is B square minus 1. So these are three effects of B at three levels of factor A. Now using these linear effects of B, we will compute the linear effect of A. So this actually represents the linear effect of B when factor A is at high level. This represents the linear effect of B when factor A is at intermediate level, and this effect here represents the linear effect of B when factor A is at low level. And we know that the linear effect of A is A2 minus A0. So using these two effects, we will compute now the linear effect of A, which is A square B square minus A square minus B square minus 1. So this effect computed at the intermediate level of B is not useful for computing the interaction between linear effect of A and linear effect of B. So this is now equal to A square minus 1 into B square minus 1. Note that this is an algebraic simplification. This we again cannot use to directly find the interaction component ALBL. We can find the interaction component ALBL also by first computing the linear effect of A at different levels of B and then utilizing those effects to compute the linear effect of B. So the linear effect of A at higher level of B is A square B square minus B square. This I will be denoting as linear effect of A at higher level of B. And now I'm going to find linear effect of A at low level of B, which is A square minus 1. So linear effect of A at low level of B. Now we know the linear effect of B is B2 minus B0. So utilizing these two effects, linear effects of A, we find the linear effect of B, we find the difference between the two. I am just rearranging the terms, and if you notice, this is same as the formula that we just obtained above, and this again simplifies to A square minus 1 into B square minus 1. Similarly, we will compute the interaction component ALBQ. So first we can component the linear effect of A at three levels of B and then utilize those effects to find quadratic effect of B. So let us first find the linear effect of A at three levels of B. So linear effect of A at high level of B is A square B square minus B square. Linear effect of A at intermediate level of B, A square B minus B, and linear effect of A at low level of B, a square minus 1. This is linear effect of A at high level of B. This is linear effect of A at intermediate level of B. This is linear effect of A at low level of B. We know the quadratic effect of B is B2 minus 2B1 plus B0. So we multiply the middle term by a minus 2 and then add the last term, and we get the simplified expression as a square minus 1 into b square minus 2b plus 1. Now if you notice in the interaction component ALBL, the simplified formula a square minus 1 into b square minus 1, the first term of this gives us an impression of linear effect of A, and the second term gives us an impression of linear effect of B. Now in the algebraic simplified formula for the interaction component ALBQ, the first term gives us an impression of linear effect of A, and second term gives us an impression of quadratic effect of B. We found the component ALBQ by first finding the linear effect of A at various levels of B. We can also find this component ALBQ by finding the quadratic effect of B at various level of A. Note that if we find quadratic effect of B and then utilize those effects to find the linear effect of A, then we have to find the quadratic effect of B only at high and low level of A. The effect computed at intermediate level of A will not be utilized. So first we find the quadratic effect of B at higher level of A. So a square b square minus 2a square b plus a square. Note that in this expression factor A is at high level always in all the treatment combination, and the level of B changes as per the formula. And now we compute the quadratic effect of B at low level of A. So it is simply b square minus 2b plus 1. This is a naught bq. Now we know the linear effect of A is A2 minus A0. So we find the difference between these two effects, and this gives us the interaction component ALBQ. And again, if I simplify this, I get the algebraic expression A square into B square minus 2B plus 1. Now similarly, we will be finding the interaction component AQBL. So I will first find the quadratic effect of A at two levels of B, high and intermediate. So the quadratic effect of A at high level of B is a square b square minus 2a b square plus b square. This is quadratic effect of A when B is at high level, and quadratic effect of A when B is at low level. So a square minus 2a plus 1. Quadratic effect of A when B is at low level. Now the difference between the two will give us the linear effect of B, which simplifies to the algebraic form a square minus 2a plus 1 into b square minus 1. Again, if you notice, the first term in this expression gives us an impression of quadratic effect of A, and second term gives us an impression of linear effect of B. Similarly, we find the interaction component AQ, BQ. So first we'll find the quadratic effect of A at three levels of B. So the quadratic effect of A at high level of B is a square b square minus 2a b square plus b square. Quadratic effect of A at high level of B. Now we find quadratic effect of A at intermediate level of B. So this is a square b minus 2a b plus b. And then finally the quadratic effect of A at low level of B. So a square minus 2a plus 1. Now we have found the three effects at three levels of b. We will be utilizing these effects to compute the quadratic effect of b. We know quadratic effect of b is b2 minus 2b1 plus b naught. So I multiply by a minus 2 the second term and add the third term. This simplifies to a square minus 2a plus 1 into b square minus 2b plus 1. Again, if you notice, the first bracket gives us an impression of quadratic effect of a, and the expression in second bracket gives us an impression of quadratic effect of b. Again, I tell you, this expression is just an algebraic simplification.